All right, number 65. A figure skater can increase her spin rotation rate from an initial rate of 1 revolution every 1.5 seconds to a final rate of 2.5 revolutions per second. Her initial moment of inertia is 4.6. What is her final moment of inertia? So what I'd say here is, okay, so initial moment of inertia is 4.6. And I'm trying to find iota prime, right? And it says that I start 1 revolution every 1.5 seconds. So what that means is if I were to work that out, right, that would be 2 pi radians every, or as a matter of fact, we can even do it in revolutions if we want. We can say run revolution every, what did it say? Every 1.5 seconds. So what is that? I think that's 0.67 revolutions per second. And my omega prime is going to be 2.5 revolutions per second. So then what I'm going to do is I'm going to say the angular momentum is conserved. That means that iota omega is equal to I prime omega prime. And you know all of those except for one. Is that all right? Now, it turns out in this case, so probably technically we should be doing radians per second. However, if you look at the units, if you keep everything in revolutions per second, it's a little bit easier. It's a less one less conversion step, and it'll give you the same answer because the units cancel out. Yes, sir. 63. A non-rotating cylindrical disk of moment of inertia iota is dropped onto an identical disk rotating at an angle speed omega, assuming no external torque was the final common angular speed of the two disks. So the idea is this one's not rotating, this one is, right? And then this one drops on that one so that now I've got two, and they're going at some speed omega prime that I'm trying to find. Okay. So I do this the same way. So I'd say we need my angular momentums to add up. And let's call these disks 1 and 2, right? This is kind of like the rotational version of an inelastic collision where they stick together. So the idea would be that L1 plus L2 is equal to the combined angular momentum of them combined, right? So they both have the same moment of inertia iota. So this is going to be iota 1, omega 1, which is, we're just calling omega, plus, you know, the iotas are the same, so I don't really have to call it iota 1, I can just call it iota. So iota omega plus iota times, this one's not rotating, right? 0. Is going to be equal to the new iota of this combined thing, which is 2 iota, right? Times omega prime. And if you look at this, right, all your iotas cancel. Actually, this whole thing cancels and all your iotas cancel. And you should get that omega prime is equal to omega over 2. Is that all right? So it's kind of like the linear version of this is that one where, remember we talked about the two train cars of the same mass, and one was moving and then it connected to the other one and they went half the speed. It's the same idea, but it's the rotational version, right? One thing is moving, the other one collides inelastically with it. So all of a sudden you double the iota. If you double the iota, you've got a half the omega. What else? I'm gonna do the review today a little bit differently. So I put it in two parts. The first part is going to be, so I think that um, this unit is heavier on concept than most units. And actually, although there is still a decent amount of math, it's probably a little bit lighter on math than most units. And so I really want to focus on the concept for a little bit. What I actually did this time is I made a review paper. We're going to do this, and then after this, I got a review Jeopardy that we'll do. But when you get this, number one is just ask you to think about what the symbols mean. And still have it marked at home. I think I have this posted. I think there's a link in today's agenda to this paper I'm handing out. What I want you to do here in number one, right, is it gives you, like, for example, part A says, let's say that the problem was giving you a number of revolutions. And ask you two things. What symbol does that correspond to? And also, are there any conversions you need to do before doing the calculation? Okay, so that's what we're going to do here, right? So if it said number of revolutions, would you have to do any conversions? If so, what are they? What symbols? And then go ahead and once you're done with that, go ahead and compare with the part that gives you three. All right. Emma Cooper, symbol for number of revolutions, theta, and what conversion you have to do. Yeah. So number of revolutions, what you're looking for is you're looking for theta, but if you've got, I've got the same multiply, but if you're trying to get theta, right, what you do is you get your number of radians. Or sorry, if you have revolutions, you multiply by 2 pi. So the revolution is a theta. Okay. Braylon, tell me about RPMs.
Omega, we have to multiply
Right. So I want to just be clear because one thing that's easy to get tripped up on in this is when you use 2 pi, when you use 0.1047, right? 0.1047 is for RPMs and radians per second. 2 pi is for radians and revolutions, right? So there's that. All right, radians per second squared. Chris, what's the symbol?
Um,
Yeah. Oh, radians per second squared is alpha. Yeah. Radians per second squared is alpha, the one that looks like a fish. Linear velocity of a point on the outside of a wheel. Gianni, what do you think? Meters per second. What symbol though? What on the equation? What symbol? V. Yep. Linear velocity. Just remember, linear terms are just regular letters. So V. Distance a wheel travels over a certain number of radians. Daniel, you got an idea about that one? Yes. Right. Because remember, the distance is ends up being the arc length traced out by the wheel. So yeah, you're looking for arc length if you're looking for distance, which is L. Oh, if you need help visualizing this, well, we'll see if it works. This might just be a way to visualize it. If something's rolling, is it going? So if it's rolling, you see that the distance it rolls is the same as the arc length it travels, right? So that's a way to visualize that if you need it. All right, moment of inertia. What's the symbol, Becky? I or iota? Angular momentum. Emma Basinger, what do you think? No, that's alpha. Angular momentum. So if you get caught up on this, what I would recommend is, you might remember what regular momentum is. P. So P, if you look for P on your equation sheet, right, which you'll have on the test, you look at the one right next to it. That's angular momentum, right? So angular momentum is L. And torque, Leo. Yeah, call it tau, but yes, that's what it is. Tau, T-A-U. All right. Next question, if you haven't answered it yet, go ahead. Let's take a moment to try 2, 3, and 4. And answer those with your partner. Drake, can I ask you about the skater pulling her arms? Yeah. So if you're decreasing the radius, right? Decreasing the radius means decreasing iota. If you want L to stay the same, right? You want angular momentum to stay the same. If you have less iota, you have to have a bigger speed. I don't think I meant to show you this video last time, but I don't think I did. My computer's being sluggish today. So what you can kind of see there, you can see as she's pulling her arms in, she speeds up. As she releases her arms, she slows down. And again, the idea is here she's got a relatively large radius, but as she makes her radius smaller and smaller, right? As she makes her radius smaller and smaller, she's going to have a smaller and smaller iota, and so she's going to have a bigger and bigger omega. Right? And then to stop, she needs to increase her radius again, because then if she increases her radius, bigger iota, smaller omega. So bringing arms in is going to go faster. Bringing arms out is going to be going slower. Okay. Oops. Well, before I go to the next slide, why is a wrench better than your fingers to tighten enough? Malachi, what do you think?
The wrench has a larger radius than the fingers.
Yeah. Yeah. So the deal is if you got a bigger, yeah, you want to maximize the torque to loosen a wrench, right? So the idea is if you've got your force at a bigger radius, you're going to have a bigger torque. Because torque is radius times force. With that. All right. What about the hoop versus the disc? Max, what do you think? Why does the hoop have a bigger moment of inertia than the disc? Yeah. So I like to think about this, right? If you have two things that are the same mass, right? But you have a hoop, right? A hoop, all the mass on the outside. You imagine if you get a disc, what you're doing is you're taking some of that mass and you're pulling some of that mass in. That's what that's supposed to show, right? It's you're spreading out the mass more, right? So there's more mass towards the inside, and since there's more mass towards the inside, the moment of inertia decreases. All right. I want you to take a moment and let's discuss. I'm going to have you discuss 5. So 5 gives you 4 objects, 5 objects, I think. A 5 centimeter diameter hoop, a 7 centimeter diameter hoop, a 5 centimeter diameter disc, 7 centimeter diameter solid steel. So I want you, if we were to roll them down a ramp like we did in here the other day, which one of those things, I want to rate them from fastest to slowest when they get to the bottom of the ramp. So you might think about what their iotas are, and then think about, and then rank those from smallest to slowest, from fastest to slowest. And go ahead and discuss this with your partner. All right. what I've done here on this slide is I've written out the iotas for each of those things, right? Now let me ask you this. What does the radius do to how fast it goes? Remember? Yeah, there you go. So from an absolute perspective, you're right. Things that have a bigger radius have a bigger iota. Now remember the demo we did with the ramp though. I had like 3 different size hoops. I had like 3 different size balls. And how did the radius affect that? Remember it didn't, right? Remember we said that mass and radius cancel out of the equation. When I'm talking about, not when I'm talking about in absolute terms, how much smaller it is, because you're right, Leo, we're talking about absolutely what has the bigger like kilogram meters per second squared or kilogram meters squared. But in terms of what gets down faster, right? Remember we did the equation, we saw that all the masses cancel, all the radiuses cancel. So radius is a red herring. Radius doesn't matter. And I also didn't give you the mass data. The mass data. Okay. All right. So with that in mind, Kelly, what do you think is the fastest? Yes. Why? Yes, and if you look at the equation too, right? The equation is 2/5, right? That's the smallest fraction, right? So the one that's going to be going the fastest, or going to get down first, is going to be the sphere, right? Because the sphere, because again, everything else cancels out. The mass and the radius, we actually solve it out, will cancel out. But the 2/5 will not. 2/5 is the smallest, I mean, it has the least resistance to turning, right? So if it has the least resistance to turning, that's the one that's going to go fastest. Solus, what comes next? Disk. Okay. Again, it doesn't matter that it's 5 centimeters because radius doesn't matter. So disk is second. Sam, third. So 5 centimeter hoop and 7 centimeter hoop is the last. They'll be the same, right? So it's a tie. These two are tied for third, right? We're okay with that. All right. All right. Little Bobby and Janie are both running a carousel. It might help you to draw a sketch to kind of keep this getting your mind what's happening. Janie is on a pony there. She's 5 meters for the second, right? Bobby is 7 meters for the second, but they're on a carousel, right? So, 2 questions. Who has a bigger V? Who has a bigger omega? So, take a moment to discuss with your partner 6. Who has a bigger V? Who has a bigger omega? Aiden, who do you think has a bigger V? Why? Yeah, he's further radius out. So if we look at this, I don't have, so this is just, I showed you this before. Oh. Sorry, I don't care what he has to say. I'm YouTube. But the idea here, right, is the person on the outside has to travel a bigger distance in an amount of time, right? So Bobby's going to have a bigger V, right? Nathan, who has a bigger omega? So I guess the question is, who completes 2 pi radians first? If I watch this equation, right? Who completes the circle first? Does it? Let's look, right? It starts here. Which one gets back to here first? They're tied. Okay. Right. He's saying something about this. I don't know what he's saying. But okay. So the idea here, right? If I start here, right, who gets to my hand first? They both complete a circle in the same amount of time. Since they're on the same turntable, right? Since they're on the same turntable, the omega is the same, right? They're both going to complete 2 pi radians in the same amount of time. In order to do that, body has to have a bigger v, but they have to have the same omega. All right, last question. This is about the demo we did last time where I was standing on the turntable. So you are holding a spinning bicycle wheel standing on a stationary frictionless turntable. The wheel is spinning counterclockwise. You can tell it's counterclockwise. Test for yourself if the right hand rule works, right? If it goes counterclockwise, you get your thumb pointing up like this. Okay? So if you suddenly flip the wheel over, what will happen? And what I mean, what will happen? I mean, which way will you turn? Why? Yes, sir. I mean, in theory, it would be that mine would have to. I mean, you don't really have, like, that has a lot of iota compared to like what it is. It doesn't have a lot of iota compared to that. I don't think it would really be noticeable. But in theory, yeah, you could. I mean, there's no reason why, if you had it perfectly frictionless, it should do something. All right, which way are you guys turning? Anyone want to tell me? But, right. So yeah, the wheel is going, when you flip it, the wheel goes from counterclockwise to clockwise. So you have to go counterclockwise. Anybody remember what your L is? How much momentum you have relative to the wheel? Yeah, Drake. It's double, right? What happens here is, right, the wheel goes from positive L naught, positive L naught to negative L naught, right? So we need conservation of angular momentum to happen. So at the beginning, I have no L. The wheel has L naught. At the end, I have whatever this L is. The wheel has negative L naught. If I solve that out, my L has to be equal to 2. Interesting question. If this was really perfectly frictionless, so I got the wheel. If this is really perfectly frictionless, I flip the wheel and I go counterclockwise. What happens when I flip it back? If it's perfectly frictionless. So I go this way. Like do it. So I do this and then I flip it back and I go this way. I don't think so. Think about it carefully. Right? You would stop. Why would you stop? Yeah. If it's really frictionless, right? When you flip it, you go to When you flip it, you go to this situation, right? And you get 2L naught. If you flip it back, you go back to that situation and you stop, right? If it's really frictionless, that's what's going to happen. Now, it didn't happen for us because that thing has so much friction that what's going to happen is you're going to flip it, you're going to turn, and then over time you're going to get back to zero, right? So then to maintain momentum, it's going to want to make it go back. But if I really had it frictionless, I flipped it, it would make it go this way at the constant rate. And then when I flip it back, we just reset to our original conditions, right? And I would stop. All right, any questions? Cool. All right, so the review game today, I want to change it up a little bit. So I've got Jeopardy today. In order for this to work, I need bigger groups than I had last time. So generally speaking, I think that we can get it by combining two groups. But here's what I want to do. I want you to take a minute. I'd like to avoid moving as many people, like as few people to move as possible. But I want you to get yourself into groups of 3 to 4. If you need to move a little bit, you can move a little bit, but I just don't want to shuffle the whole time. So find a group of 3 or 4. What are we thinking here? Okay. And 8 of you have a group. What's the group back here? You just have to. Okay. 8 more. What do we got over here? 1, 2, 3, 4. 1, 2, 3, 4. Go ahead. 4. 9 here. 1 and 2 is three. Cool. All right. Send one person out from your group to get a whiteboard and a marker. And Excel. All right, how many groups? 1, 2, 3, 4, 5, 6. I think I got 7. All right. At the end of the period, I'll show you how you can get to this to do your own studying later on. But for now, team 1. So Emma, do you guys have a team name? All right. I'll give you guys a chance to choose a team name, and then we'll get our team names up here. So. Hey, are you on the team? Yeah, all right, you guys have a lima beans. Who is next? Drake, what's your group name? Is that B-E-Y? All right. Malachi.
Draft bag.
All right, where are we at now? Sam, what's your team name? Gold Shark. Danielle, what's your team name? Blue. All right. Chris, have I gotten your team yet? What's your guys' team name? Sure. Did I give everyone team? I made too many teams. That's right. All right, here's how this works. All the categories that don't say timed, it's going to be like you're going to write your answer and I'll come around and check it. The categories that do say timed, I'm going to put it on the board. I'm going to give you, let's say, 30 seconds to write on the board, and then you're going to all hold them up at the same time so that I can grade it. That's what's happened for the time columns. You can't lose points in this game. You can only gain points. And we will start with line of the what's your for 100. All right. So everyone gets to write this on. Every team gets to answer this on their board. What would happen? So 2 questions. What would happen to an object with no tangential acceleration, but a non-zero radial? Remember, radial means centrifugal, right? So what would happen to an object with no tangential acceleration, but non-zero, that is, not zero, radial acceleration? What would happen to an object with no radial acceleration, but a non-zero tangential Yeah. Remember, radial means centripetal. What do you hear? Oh, also, I'm a lazy Jeopardy player, so I don't care about that.
I'm not really. So what is? What is your like the answer? No, right? Oh, I didn't do that part. So it has no rate. So it's not.
I don't have your guys.
Why? Okay. We.
No.
Okay.
Blue, do you have an answer? That's
So it's going higher.
You're on it.
All right, right. If you've got a tangential acceleration, right, that just means you're changing speed, right? Tangential acceleration means you're changing speed. Centrifugal acceleration means you're changing direction. That just means you're going in a circle, right? So what I say, number one, you're spinning in a circle at a constant rate. Number two, accelerating in a straight line, but not going in a circle. So Lima Beans gets points, Beyblades gets points, Gold Shark gets points, if I can get to it. Blue gets points, Sure gets points. All right, Beyblade, what do you want? For 100. Which has more kinetic energy, a rolling disc or a rolling hoop? Assume they have the same radius, mass, and translational velocity.
Yeah. Yep. Yeah. All right. So again, if they have the same speed, right? If they have the same speed, so the equation is 1 half iota omega squared. They have the same speed, they got the same omega, but which one has the bigger iota? The hoop. So, well, so the hoop has more kinetic energy. That's a lot of work to just say if you've got it, that mr squared is bigger than 1 half mr squared. All right, Lima Beans, Beyblade, Grab Bag, Gold Shark, and Sure. All right, Grab Bag, what do you want? For what? All right, so this is how this is gonna work. I'm gonna get a timer for 30 seconds. Let me get it ready here. You're gonna write it on your board, and when I say to show it, you're gonna put them all up in the air so that I can see it. So here's the question. Time starts when I finish reading it. If you double a flywheel's rotational speed, by what factor will its rotational acceleration increase? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is interesting because I'm looking at this and I'm trying to understand what this is asking. But that's not what it says. It says by what factor will it's, that should say rotational kinetic energy. I think that's a bad question. It's a bad question. It should have said if you double the flywheel's rotational speed, by what factor does the rotational
kinetic energy increase, in which case it would be 4. So it is 4, but that wasn't the question for that. It was the question for yeah. I'm sorry, that's my bad. I wrote that. Okay, no points for that one. That's my bad. Grab bag. Grab bag. Do you want to pick a different one? All right. Okay. You are spinning a bicycle wheel while standing on a stationary turntable. If you suddenly flip it over so that it's spinning clockwise, what will your turntable do? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hold on there. Yes, 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 no, yes. So if it goes from counterclockwise to clockwise, then the turntable is going to go counterclockwise. This thing's in my way. I'm going to have to move this thing. So again, so the thing went to L. The table must have 2L upwards. Okay. All right. Where are we at? Gold shark, what do you want? Quantities for 400. Ooh. All right, same plan. Symbol and units in order of torque. So symbol and units of torque, moment of inertia, rotational kinetic energy. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Boards up. Not quite. Not quite. Not quite. Yes. Yes. Is that thing meter meter squared? Where? No, it's not a meter squared. It's a meter squared. So I think that was you gotta help me out. I think Lima Beans got it. I think Beyblade's got it. I don't think anyone else got it. Yeah. So torque is tau. I couldn't type symbols on this, so torque is tau, which is meters newtons. Moment of inertia is iota, which is kilogram meter squared. Rotational kinetic energy is KER, which is joules. Okay. Kinetic energy is the one where it's the same as it is translational. All right. Blue, what do you want? Rank the following from largest torque to smallest torque, assuming the force is the same. Yes, I know there's no F2. I don't know why. But largest to smallest. I don't know. I got the image from the book.
Where the heck is you? Why is this missing? Apparently. Yeah.
Yeah, but it's, yeah. Yes. Yep. All right, good, right. Perpendicular forces are the biggest. Then this one has at least some perpendicular component. This has no perpendicular component. All right. Where are we at? Sure, what do you want? 400. Suppose that the speedometer of a truck is set to read the linear speed of the truck, but uses a device that actually measures the angular speed of the tires. If larger diameter tires are mounted to the truck instead, how will that affect the speedometer reading? Okay, does this make sense? So the idea is the speedometer really measures omega and then does some sort of conversion to turn that into V, right? The question is, if I put bigger tires, but I don't do anything to reprogram the speedometer, is the speedometer going to read the right speed, a higher speed, or a lower speed? You're thinking too much. It will read a higher speed even though the speed of the truck is like technically if it's going 40, it might read 45. Higher speed than an egg. Would tell me which one. What are you guys trying to do? Like your food, looking at higher R. Yeah. Test it out. You'd be a higher speed. Speedometer will be a higher speed. Oh. So if you think about let's see how I explained it. Okay. So the way that I think about it is so you've got B equals R omega, right? Your speedometer is expecting a certain R that's low, right? So your speedometer is expecting a certain R. Oh, for a given omega, your actual speed is going to be bigger, right? Because you're plugging in a bigger R. So if you're plugging in a bigger R, the speedometer is going to underestimate. Here's another way to think about it, right? In a smaller wheel, let's say you have a wheel that turns once in a meter, right? If you get a bigger wheel, if you go around the whole thing, you'll have gone further than a meter, right? So you'll actually be going farther than the speedometer thinks you have gone. So points go to Beyblades, Grab Bag, Gold Shark, Sure. All right. Who chose that one? Sure did. Lima Beans, what do you want? For 400. Two spheres have the same radius and equal mass, but one is made of solid aluminum and the other is made from a hollow shell of gold. Which has the bigger moment?
They literally paid for a it would be better to do it right.
Yeah. I just want to get there's a new one here. Because it's not a food, it's a food. It's not a food. So it's not actually going to be a solid. And it's solid.
Everything ever.
Why? Yep. Right, if all the mass is on the outside, you're going to have a bigger moment of inertia. All right, Team Beyblade, what would you like? Why does an ice skater spin faster when she pulls her arms in? Yeah.
No, they saw your they saw your movie. They were like, oh my god, great.
Yeah. All right, good. Radius is smaller, iota is smaller. This leads to bigger omega. All right. Grab bag. What do you want? All right. Let me get my timer ready. All right. A solid cylinder of radius 20 centimeters and a solid sphere of radius 35 centimeters are released at the same time from the top of the ramp, which will reach the bottom. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Boards up. Yes, 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 yes. So the solid cylinder, by the way, solid cylinder is just a disc, right? Solid cylinder is a disc. All right. Who get Gold Shark? What do you want? Okay. So here's a this is a dumbbell in outer space. Okay, so there's no friction or anything. A force is applied to a dumbbell for a certain period of time. First as an A, where it's pushed to the center, and then as in B, which it goes from the top. In which case does it acquire more kinetic energy? Case A or case B? Make sure you have an explanation for this one. So you're thinking about it right. Iota is the same. They have the same. So iota is about the object, not the force. All right. The correct answer here, there are actually, I would say that most groups were thinking about it correctly, but maybe didn't draw the right conclusion. So one of these things is going to rotate. Which one's going to rotate? B is going to rotate. So B is going to rotate and translate. A is just going to translate. You need more energy to rotate and translate than you need to just translate. So Beyblades and sure. Blue, what do you want? Bonnie sits on the outer rim of a merry-go-round. Clyde sits midway between the center and the rim at r equals 2. Bonnie has an angular velocity of 12 and a tangential velocity of 10. Calculate Clyde's rotational and tangential for 2 questions. I want Clyde's V and I want Clyde's omega. I told you about yeah.
So, you know, What if you just have to get
Yeah.
and then we're finally like how does the angular velocity is omega squared times r? Why is it? Yeah. You're not looking for the oh, my bad. My bad. That was in the joke. I'm keeping the five. I was trying to tell you. Is that radians per second? Yeah. Gotta get lit.
All right. Yes. Yes, but I think you can get that number. Well, you can't get the rate, but you can get the number.
Oh, wait, no. Oh, I did.
Yes, but I think you can get that number. Look at it carefully. Look at what you've been given. Carefully do that. Yes. So there's one other thing.
There.
Okay. You haven't done anything.
I just want to be about I think until my college that the test is going to be after. No,
Yeah. Yeah. So, yeah, there's an easier way to do that work. But the easier way you can do that is you can say it's going to be after. Full start.
All right, they have the same omega, right? So the omega is 12. If you're at half the radius, you've only got half the velocity, so it's 5. So lima beans, Beyblades, grab bag, blue, sure. All right, who chose that one? Blue chose that one? Sure, what do you want? Grab bag 400. Okay, I'm actually not, I'm going to give you, I'm not going to time this one because it's a lot. Rank from largest to smallest angular momentum. There may be ties. So I'd like to see, the way I'd like your answers, I'd like it to be like 1 is greater than 2 is equal to 3 is greater than 4. Something like that, right? So. So I want to know absolutely which one's the highest, which one's going to be the ground. Hey guys, I want to be clear about this. I want to know absolutely if you measure it, which one's the biggest. I don't want to know which one is the ground. So in other words, radius and mass do matter. Radius and mass do matter because they're not going to cancel out.
This was for exercise.
Well, you don't need more. Wait, maybe I marked the wrong way. No. Okay, what is that?
So 3 and 4 are tied. 1 would be the third. 2 is not.
Yeah, that is correct. All right, we had one group get that one right. Congratulations to Team Sure. This is what it should have been, right? Here is how we do that, right? So L is iota omega, right? Iota for a cylinder is cylinder is a disk, right? MR squared. So the first one has MR squared omega. That's the L, right? The second one is 1/2 MR squared omega. The third one is 1/2 M quantity 2R squared omega. So that means it's 1/2 M 4R omega, which is 2 MR squared omega. And if you do the fourth one, it's also 2 MR squared omega. So it's 4 equals 3 is greater than 1 is greater than 2. All right. If you would like to look at this at home, I'm going to show you where you can find it. So in our, I have to actually unlock it for you because I don't have it unlocked yet. But if you go to the yellow folder, the chapter 8 folder, practice problems and pages, I will publish this for you right now, publish for period 1. So if you click on this link, you can go through here, right? You can even play a game with your friends if you want, but really all you need to do is you click them, you press what do you do? You press space bar to reveal the correct response, you press escape to get back to the questions, and that's how you can study that if you'd like. Test next time, homework due next time. Projects when we get back.